Hey there. What we're going to talk about in this video is the mean value theorem. And we went through this in our notes the other day, but the mean value theorem says that if you have a function f and it is continuous, this is important, these little details, on the closed interval, that's what those brackets mean, AB, so AB is an interval in the x direction, and if it is differentiable on the open interval AB, then there exists a value C in the interval AB such that f prime of C, meaning the instantaneous rate of change of the function, or the slope of the tangent, equals f of b minus f of a over b minus a, which is this is an average rate of change. So the mean value theorem, if these conditions are met, that it's continuous on the closed interval AB and it's differentiable on the open interval AB, the mean value theorem guarantees that this will be true for at least one value of C in the interval from A to B, saying that the average rate of change will equal the instantaneous rate of change, which is what our derivative gives us, for at least one value of C. So if you were driving from here to Anchorage and you are averaging 60 miles per hour, sometimes you're going to be going less than 60 miles per hour, which means that sometimes you have to be going more than 60 miles per hour. The mean value theorem tells us at some point, if your average speed on your trip was 60 miles per hour, at some point in that trip, you had to be going exactly 60 miles per hour. All right, so let's do a couple of examples here of how to use this. And then we'll talk about Rolle's theorem. All right, which is a special case of the mean value theorem. So here's my function, f of x equals 5 minus 4 divided by x. Find all values of c in the interval from 1 to 4, and so these are x coordinates, 1 to 4, such that the derivative, we're going to find, this is a particular value of x that we're going to find where that instantaneous rate of change is equal to the average rate of change, which is this. So you guys, when you're looking at f of 4 minus f of 1, so basically what this is saying is, if you have when x is 1, so we can call that x1 instead of, well, here, let's just do this. So the y-coordinate associated with x equal to 1, we can call f of 1. And that's our y-coordinate, y1. And then we have another point, when the x value is 4, the y value is f of 4. This is my second point, so I'm going to call it x2, y2. So this is just the slope. We're talking about back in Algebra 1, when you wrote slope like this is the same thing, just in function notation. So this is my change in y, and this is my change in x, and so it's the average rate of change, or the slope of a secant line, and this is the slope of a tangent line. Okay, so what we need to do is look at what this is asking us to do here. Even if you didn't know what the mean value theorem is, if you can understand this notation, you can still do this problem. F prime of C means find where the derivative, so we need to find the derivative, so let's find f of x, f prime of x. The derivative of 5 is 0. So we have to find, you know what, I'm going to rewrite f of x first. So I have 5 minus, and I have an x in the denominator, it's 4 divided by x. Let's bring that up, and to do that, it's going to change the exponent to a negative. So f of x can be written like the original, or we can rewrite it like this, which is going to make it easier for us to take the derivative. So let's find f prime of x. The derivative of 5 is 0. Drop the negative 1 in front. Negative 1 times negative 4 is going to be positive 4. and that becomes negative to the negative second power. And when I rewrite that, it's 4 over x squared, because now I need to evaluate that. Now I'm going to have to, that's what's going to go here. We're going to have to figure out what value of x makes it equal to this, which is telling us to find the slope between 1 f of 1 and 4 f of 4. So we need to find, excuse me, we need to find f of 4 and we need to find f of 1. So f of 4, if I put 4 in here, I get 5 minus 4 divided by 4, which is 1. So 5 minus 1 is 4. And f of 1 is 5 minus 4 divided by 1, which is 1. So I have these two ordered pairs, 1, 1, and 4, 4. So if I plug that all in, my f of 4 is 4, my f of 1 is 1, and I get over 4 minus 1. So that ends up being 3 over 3, or 1. So we want to find, when does this average rate of change equal the instantaneous, when does the instantaneous rate of change equal the average rate of change, which was 1. So solving this for x, I want to multiply both sides by x squared, and I get 4 is equal to x squared. Take the square root of both sides, and we're talking about just the interval from 1 to 4. Our x coordinates that we're looking for this in is between 1 and 4. So I don't need to do the negative piece, but it's, so we get x is equal to 2. Okay, so this is the graph of our f of x, which was 5 minus 4 divided by x. The graph has a vertical asymptote at 0, but we're just talking about, so if it would have been outside of, like, so we're looking at the interval from 1 to 4, and f of 1 is 1, so right here, do a different color, and then f of 4, which if I trace to 4, 1 second here, that's this point right here, and back here. So two things need to apply for the mean value theorem to work, or to be guaranteed, and that is that the graph has to be continuous on the interval from 1 to 4, which it is, and it has to be differentiable, which it is, on the open interval from 1 to 4, which it is. So had the interval gone from a negative value of x to a positive value of x, then the condition would not have been met, and the mean value theorem cannot be applied, or at least it cannot be guaranteed. So what we did, f of 4 minus f of 1 over 4 minus 1, was finding the slope of the line between 2 points, which is called a secant line. So, and we found the slope for that was 1. The mean value theorem guarantees that somewhere in the interval, between 1 and 4, the slope of the secant line is going to be equivalent to the slope of the tangent line. That's not a very straight line, but hopefully you get the idea. And that value of c, where it's tangent, we just found was 2. So if I trace now to 2, right there is where the slope, the instantaneous rate of change is equivalent to the average rate of change between the two green dots. That's what the mean value theorem tells us. All right, so let's do another example here. So first here, in this example, we're looking at can the mean value theorem be applied? This is a polynomial, and all polynomials are continuous everywhere. So we're looking to see if it can be applied, then f of x is continuous on the interval from 0 to 2 because it's continuous everywhere, and every polynomial is going to be a smooth curve, and there will be no cusps or corners, and we already know that it's continuous, but we also know that it's differentiable everywhere, but in particular for this problem on the open interval from 0 to 2. So if so, so it is, the mean value theorem can be applied because these two conditions are met. So if so, find all values of C in the open interval from 0 to 2. So this is my interval here, A, B. So A is 0, B is 2. We need to find where the derivative is equal to the slope between the 2 points that are associated with x equals 0 and x equals 2. So let's find the derivative. So f prime of x, that's supposed to be an equal sign there, is 4x cubed minus 8. And we want to know when that is equal to f of b, so this is my derivative. And I could put a c in here. I'm finding a particular value of x, so that's why they have a c in the theorem. You can leave it as an x if you want to. But so we're going to find, we need to find f of, we need to find f of 4, or not 4, f of 2, still thinking of the last example, f of 2, because we're going to replace, remember this is my interval, this is my a and my b, so I'm putting in 2 here for the b, and I'm going to put in 0 here for the a. Same thing in the denominator, so we're going to find f of 2 minus f of 0 over 2 minus 0, and f of 2, so let's find f of 2. We have 2 to the 4th minus 8 times 2. I'm just plugging in 2 here. And so f of 2, we get 16 minus 16, which is 0. And let's look at f of 0. It is 0 to the 4th minus 8 times 0, which is also 0. So we end up with, the slope is 0 over 2, which is still 0. So now we have to figure out where 4x cubed, where does the instantaneous rate of change equal 0, which means we have a horizontal tangent at that point. So we need to solve this right here. 4x cubed minus 8 equals 0. So we're going to add the 8. Divide by 4. We get x cubed is equal to 2. And we need to take the cube root of 2, and that is the place when x is the cube root of 2, the instantaneous rate of change will equal the average rate of change, which is 0. So earlier I talked about, we would talk about the Rolle's theorem. Well, Rolle's theorem is a particular case of the mean value theorem, and it's when the slope is equal to 0. So he came up with this first, and then the mean value theorem was more general because you can, it doesn't have to be a slope equal to 0. But I'm going to graph this really quickly. So this is the graph of x to the 4th minus 8x. And if I trace to where x is 0, it's this point right here. And tracing to where x is 2, it's the other x-intercept there. So the slope between those 2 points is 0. That's the slope of the secant line. And the location of the tangent line that is equal to 0 is right here. And this value of x should be the cube root of 2, because that's where we found the instantaneous rate of change was also equal to 0. So if I trace here, if I trace to where x is equal to I need to take 2 to the power of 1/3, which is the same thing as the cube root of 2, you can see that it's at that point where you have a horizontal tangent and the slope of the instantaneous rate of change is equal to the average rate of change.